Okay, hello everyone, and welcome back to my lectures about power system analysis and this specific series of videos. This series dedicated to the introduction to DC transmission systems. We are covering the topic of HVDC technologies, okay? And right now we will talk about HVDC transmission system configurations, okay? Again, I am a power system engineer. I'm not a power electronics. As a consequence, if you want to have more details about power electronic devices, the effects inside the converters, commutation technologies, etc., PWM, space factor, anything like that, please, this is not the video for you. You must go to power electronics books and probably you will get a deeper explanation about that, creation of harmonics or source or power quality issues and so on. No, I am a power engineer, and as a consequence, for me, a power converter is a technology that we use for providing solutions for power systems. And that is the reason that this explanation is basically oriented from the power system point of view, okay? Well, let's start this discussion, and let's go here, and I will show you basically topologies that we can find regarding HVDC transmission systems, okay? Here at the left-hand side, you can find the classical monopole configuration, okay? The monopole is basically because we have a signal between reference and a positive or negative voltage, okay? In this case, you can see reference here, like the grounding point here, and you can have a pole, and that could be positive or negative depending of the interest, okay? And this is the most basic configuration that is called the ground return, okay? In a minute I will discuss more, but as you must know, when we have DC signals, the current is going in one direction in one pole and is coming back on the other, and we call this the classical ground return. Here we have the metallic return because there is a physical metallic conductor creating the return. It's not the earth. Here we have two, basically is the monopole with midpoint grounded, okay? This is a monopole configuration, but still having a grounding point for returning some currents. And here we have a back-to-back configuration, okay? On the other hand, here in the middle, you can see the configuration. There is a letter P, and that is a bipole. The bipole can be different topologies, the basic bipole, and we have here bipole with metallic returns, or we can have several converters, converter bridge in series in order to create a bipole configuration of series connected converters, okay? And finally here on the left-hand side with the letter C, you can see a multi-terminal configuration. Multi-terminal configuration is probably the most recent configuration. It's basically when we use a resistive network to interconnect multiple sources, okay? And the multi-terminal configuration, it can be 3, 4, 5, 6 poles depending of the converter station, depending of the configuration, okay? Well, let's start with the basic one. This is the monopole configuration, and the monopole configuration, as I said before, is the simplest and the less expensive system for relative low power transfer, okay? As you can see over here, we have, this is the configuration using a metallic return, okay? We can have here, for instance, a copper, a cable here, and over here in blue color, we can have another cable, and that is the return, okay? What I'm telling you is that we have, for instance, two conductive mechanisms. It could be cables, or it could be, for instance, the blue one on the top could be the cable, or below could be some pipes or some other structures that can be used for the return, okay? But typically it's a metallic return. It can be a cable, okay? But in this case, what you need to know is that we have here a ground point, okay? When we have this ground point, the idea is that we are including 0 here as a reference, okay? When we use this kind of polarity, when we use the monopole link, typically what we do is, in order to minimize the corona effect in the DC line, well, the negative polarity is the one that is less affected by the corona effect. For that reason, is typically operated with negative polarity here, and the positive is going to ground. Okay, that is one of the explanation over here. And here we have the ground connector. The ground return, sorry, is basically we can have a wire, a cable, and over there is where we have one polarity that is moving the current, and the other one is earth return or ground return, okay? Advantages of disadvantages. Well, the ground return is involving the ground, and you don't have full controllability about the grounding resistance, okay? And there is a possibility of having some voltage drop that it's bigger across the grounding return, okay? But the other issue is here regarding those electrodes, okay? Those electrodes, they will receive a lot of current at the converter station, and as a consequence, the electrical stress over there will be high. There is a possibility of corrosion over there, and also it could be unsafe for people working around on the near to those electrodes, because the step voltage, the voltage at the ground, it could be dangerous high, okay? Some of those applications are typically for low voltage, and in some cases people use electrodes by using the C as one mechanism to keep control of the voltage drop across the earth, okay? The most useful of those configuration is basically the monopole with metallic return, okay? That is typically the configurations that we want, and is because we have control of the voltage drop in both poles, and that is something that we want in order to minimize some harmonic interference and some corrosion, okay? Another option is avoiding grounding one of the poles. That is the case of the symmetric monopole. We have two specific poles. However, there is no ground point in any of them, and in that case, the problem is the possible voltage elevation at the configuration, okay? And that requires some insulation levels that could be very expensive and prohibitive high, okay? And another thing is, in this case, because they are not contact with ground in any of the converter station, this system is able to manage in some way some faults, okay? However, again, the voltage control, it could be a problem, and the insulation levels also, okay? An alternative to the previous system is including a midpoint grounded, okay? As you can see over there, they are monopole, but both of them, they are going the currents on the cables at the same direction and using the ground to return the currents, okay? And that current is basically the currents that is the sum of the current going through the lines, okay? This configuration is especially useful if you are using LCC converters and you are using the classical 12 pulse converter. In that case, you can use different impedance for the lines, and you can keep the balance of the voltages of those poles, okay? Over here I have the back-to-back configuration. The back-to-back configuration is typically a configuration when we have inverter and a rectifier and they are located at the same place, okay? You can imagine like the rectifier and the inverter located at the same space, or there is a very, very short line here interconnecting the inverter and the rectifier, okay? As I presented in my previous slides, one of these applications is when you are interconnecting systems with different frequency. One system in this side could be Brazil, the other one could be Argentina or Paraguay or Uruguay, the other side, 50 and 60 hertz. They cannot match together, and using AC line is impossible. That is the reason for using this back-to-back converter, okay? It could be quite interesting, but back-to-back converter, they have many applications, okay? For HVDC systems is basically when we have systems with different frequencies, but for PV system, for wind turbines, back-to-back converters also, they are quite useful, okay? As I say before, one of the applications is connecting asynchronously connecting two power system, one with 50, one with 60. I say you early before, Itaipu, Brazil, 60 hertz, Paraguay, 50 hertz. You can reduce the total cost, putting together the converter station, and you can reduce also losses, okay? And the transformer size can be reduced, okay? Now, I will talk about transmission system configurations using homopolar or monopolar configurations. And here, the first one that you can see, this is the ground return. And as you can see here, this is a voltage and positive voltage, sending current here and going back to the ground. And again here we have here a pole, and this is sending voltage, current going through, and it's returning the current using the ground, okay? It could be metallic returned, or it can be also ground returned, okay? What is interesting of this configuration is that the cables that we use here and there, those cables have the same polarity, okay? In this case, we are saying that the polarity is positive on the top and positive on the converters below, okay? Okay, here we have the configuration bipolar. In the bipolar configuration, right now we have here a converter, and you can see we are sending signal in this, sending current in this direction, and the other two converter station, the polarity in this case is going to the ground point, and you can see that the return current is moving through this other cable, okay? And right now, as you can see, this is a different configuration. This is a bipolar, because you can see in this case the cable is located at the positive terminal, and this cable now is located at the negative terminal, okay? Of course, we can include a ground return. That ground return in normal conditions, it will be 0. Okay, the current going through that grounded return is 0. Okay. However, we can use metallic return over there with very specific interest. Okay. If we include a metallic return, there is a possibility of using that return when there is a contingency, okay? For instance, here, as you can see, we have those lines in here represent a fault, okay? If we have a fault in this DC cable here, we can open this converter, we can switch off this converter, and the other two converter stations will keep closing the loop using the metallic return and will keep the system working, okay? What I'm telling you is if we have a fault in a cable and we have this bipolar configuration with metallic return, well, we can keep working with one of those converter stations, with two of those converter stations, sorry, and the system will keep working, okay? On the other hand, what's happened if we have a fault on converter station? Okay, if we have a fault on converter station for any reason, those converter stations on the top, they fault, well, we can open here the switches and we can still using those cables, okay? As you can see, the polarity here is still the same, but right now we are using the grounding point to connect with the other terminal and sending signal to the other converter, okay? This is a possible option. This is another possible option when we have a converter outage, okay? What you need to know and what you need to understand is that they are switches located on those cables that must allow the interconnection of the ground return and the cables in order to fulfill this configuration, okay? Well, in many cases we have very high power, okay, and very high voltage. And when we have very high voltages, well, we can start to use a series of connected converters, okay? It's quite typical that for 400, 500, 600, and 800 kV, we start to put together in series high power converters, okay? The idea is that increasing the number of bridge in series or converter in series, we are adding voltage, okay? And that is the reason for using this configuration over here, that we are duplicating the voltage. If you can imagine one of those devices using 300 kV, plus 300 kV, we are reaching here 600 kV, okay? And what is the idea of those switches here? Well, those switches that they are located in a shunt connection to the converters is basically if this converter go out of operation, we can disconnect this converter and this converter, and we can switch those, we can close those switches and keep using the other cable, okay? The idea is that the cables can still in use inside the configuration, okay? Well, now I will talk about some multi-terminal configuration, okay? Multi-terminal configuration using bipolar HVDC converter stations, okay? As you must be aware, they are multi-terminal configurations. They are quite new, and especially because when you have multiple connections, multiple in-feeds or multiple sources, one of the issues is basically dealing with the faults, okay? If we have a fault in the DC system, the problem is not the short circuit current. The problem is having the circuit breaker to disconnect the faulted device, okay? However, a few years ago, ABB and another companies, they present some prototypes and some patents related with DC circuit breakers, okay? What I will do now is a discussion about topologies for multi-terminal connections, okay? And over here, you can see a series connection, okay? How do we recognize that this is a series connection? Well, we recognize that this is a DC series connection because the current moving through some converters, they are the same, okay? As you can see, the current IDC is going to one converter, they keep going. This is a series connection, okay? In this series connection, you have bipolar converter stations, and you can have some grounded middle points, and that middle point, it's only one, and that can be used in some first to having a reference inside the HVDC system, and also for in the case of a fault or outage of one converter station, you can have the possibility of using earth of return. Okay, as you can see over there, there is series. The current is going across this loop over here through this loop over here. Okay. But now I am showing you, you can see over there that is a parallel connection, and I use red and blue color because with the red color you can identify the positive, and with the blue one you can identify the negative one. Okay, why do I say this is a parallel connection? Because in this node you have one converter coming here, one converter coming here, one converter coming here, and another converter over here. This node have 4 branches, and this node have 4 converter station. Okay, and as you can see here, you can see in the positive terminal, 4 currents going to this node, and Kirchhoff current law is still working over there. Okay. Some people call this configuration radial configuration, and other people call this configuration parallel interconnection. In this case, we have a converter station with the ground return, and you can see here all of them sharing the connection point, and that is what we call a radial parallel connection. Okay. And over here you can see the mesh connection, because again we have having converters with return using ground, but in this node we have 2 converters, and then going to another node, and there are 2 more converters, and then going to another node, and there are 2 more converters. As you can see over here, the current in this branch is coming from 2 converters. That is a typical mesh connection. Okay. Well, to close these classifications of multi-terminal DC connections, we must recognize that the HVDC technology that can be used for multi-terminals it could be the LCC or the classic, the voltage source converted, that is the favorite for multi-terminal connections, and hybrids. What is hybrid? Hybrid is a mix between voltage source converter and light commutative converters. Okay, we can use homopolar, monopolar, or bipolar configurations. We can use metallic or ground return depending. We can use parallel or series connection, and if we are using parallel connection we can have radial or mesh. Okay. Well, here I have a small summary. Thank you very much for watching this video. In this chapter, I present an overall comparison between DC and AC high voltage, okay? HVDC and HVAC. I present also the main applications about HVDC transmission system, interconnected asynchronous system, embedded into the AC system, and point-to-point connection. Then I present some introduction. I presented some introduction about power electronic converters. I'm not an expert. It was very light, very sensible, basic explanation about converters, commutation concepts, some introduction about PWM. And also some basics about commutation techniques and the use of those converters. Okay, then I went for a description of the main topologies, working with monopolar, bipolar, and multi-terminal. And then I did a short explanation about multi-terminal configurations, okay? Series and parallel, and regarding the parallel connection, I discussed some of the most used, that is the radial and also the mesh connection, okay? Here are some references. Here, if you want to have a look about LCC, go to WIDI. If you would like to have a discussion about the HVDC using voltage source converter, please read the book of Tim Van Herten and Oriol. And Vijay Sot, a collaborator of mine, he has one book, 2004, but is one of the first very good book about HVDC, especially for line commutated LCC converters. Okay, LCC. Well, it's been a pleasure having you in this series of videos about the introduction to DC transmission systems. I hope you like it. Please leave your comment below. And if you want, keep the track of my videos, and we will keep talking about HVDC systems. Thank you very much for watching this video. Bye now.